the laser.
I think there's the green.
Afternoon, everyone. My name is Keming. I'm an Eric Administration AI and Science Fellow at UCSD. And apart from AI and machine learning, I'm also a frequent Keck user. And today I'm going to be talking about our recent discovery of a Earth-mass planet and a brown dwarf orbiting a white dwarf. So our sun is currently approximately halfway through its life cycle. It was born around 5 billion years ago. And in another 7 billion years, it'll evolve to become a red giant, expanding to more than 100 times to engulf Earth's current orbit. But that doesn't necessarily mean that Earth itself will be engulfed. This is because the red giant sun loses a substantial fraction of its mass, causing planetary orbits to expand at the same time. So this plot shows the size of the red giant sun versus the planetary orbits. The red curve shows that Mercury and Venus will be engulfed right before the sun reaches the red giant branch. On the other hand, the green curve shows the surviving outer planets whose orbits expand in response to solar masses. But as for planet Earth, whether or not Earth can survive, whether or not Earth can avoid being engulfed, is still debated. It's likely that its orbit will expand just enough for it to avoid being engulfed. And if that's the case, it'll likely end up around the white dwarf sun at approximately 2 AU, twice its current orbit. So this makes our discovery quite exciting because we found a 1.9 Earth mass planet orbiting a half solar mass white dwarf at approximately 2.1 AU. So around where we would expect to find planet Earth if it could survive, avoid being engulfed. There's also approximately 30 Jupiter mass brown dwarf at a wider orbit. The progenitor system most likely consists of a sun-like star with the planet at around 1 AU and the brown dwarf in between Saturn and Neptune's orbit. So really some pretty analogous to our current sources. But I wouldn't want to give us too much hope because our Earth will likely become far uninhabitable with all the oceans of vaporize due to greenhouse effect long before the sun has become a red giant. And if I could live to see that day, I probably want to move to Mars or a Titan, or maybe do some rockets to push Earth to a wider orbit. But that's probably beyond the scope of our study. The system itself was detected in a microlensing event that occurred back in 2020 when the system passed in front of a background star, which we call the microlensing source star. And the lens in this microlensing event is pretty spectacular because the lens and the source stars were nearly perfectly aligned, which caused the background source star to be magnified by over 1,000 times to a peak brightness of around the 11th magnitude. The right we're seeing the light curve progressively zoom in from top to bottom to the peak of the light curve to at a peak magnitude around 11th magnitude. And these high magnification microlensing events are really sensitive to planets and other companions. And the original light curve analysis published a year after the event showed the lens system included both the planet and the brown dwarf. But because the lensing effect only cares about the mass of the lens system and its spatial configuration, how it could be inferred is that the primary lens has around 0.5 solar mass and is at around 1 kiloparsec. In this mass range, we can infer that this is going to either be a main sequence star or a white dwarf. And the implied brightness differ by 7 to 8 magnitudes. And because around 10% of microlensing events are expected to be caused by white dwarf lenses, we then set out to determine whether the planet host could be a white dwarf by directly measuring the lens flux using Keck. Here you're seeing a sequence of 2 images taken at the event location. before, during, and after the event. So let's take a look at the middle image first, which is taken during the peak of the event. And you can clearly see the magnified source arc in the center. And from the magnification profile, the unmagnified baseline source brightness was inferred to be around 17th magnitude in the infrared K band. And as for the left image is a scene limited image taken more than a decade before the event by the Ogle survey. And as you can see, it's pretty difficult to resolve the event location because of blending in the crowded galactic bulge fields. So this is why we propose for Keck to use so the right figure, the right image is our image taken with the Keck laser guide star adaptive optics 3 years after the event. And we can clearly resolve the event location. And not only that, we measure total brightness at the event location to be basically identical to the unmagnified source brightness itself. And just because of how recent the event is, the lens and source stars are expected to be well aligned within the Keck PSI. So because of this, we're able to reject all possible main sequence lenses, luminous main sequence lenses, and conclude that the main sequence the primary lens object must be a white dwarf, a faint white dwarf. So that's a brief overview of our discovery. The paper was just put on arXiv last week, and it's a pretty short paper. Tells a pretty interesting story. So I invite you to take a look at it if you have some time. So in the paper, we talk about some alternative evolution histories of the system that's caused by some microlensing degeneracies. And also microlensing planet usually microlensing usually only measures the projected planet separation. But here we're able to determine the physical separation of the planet based on orbital motion effects in the microlensing light curve. So instead of going into these technical details, I wanted to put our result in a broader context and discuss some future prospects. So our system is only the second microlensing planet with a confirmed white dwarf host. But soon microlensing will be able to deliver a large homogeneous sample of planets orbiting white dwarfs with the launch of the Roman Space Telescope in just under 2 years. Roman is predicted to deliver around the 1,400 bound planets in wide orbits, mostly centered between 1 to 10 AU. And this region of sensitivity is really good for studying, probing the population of planet orbiting white dwarfs, because it is exactly straddled between the inner engulfed region and the outer surviving region. Because of the large number of white dwarf lenses out there, Roman should be able to deliver a large sample of planets, large sample of marginally surviving planet, just like our own discovery. And I expect this sample to be really important for studying post-main sequence evolution of planetary systems. Another interesting aspect for Roman is that Roman will be observing from space, which means that it's going to be diffraction limited, and it's able to constrain the lens light on its own. It's not relying on follow-up observations like ours. It'll be possible to immediately identify some of the planets with white dwarf hosts. But I would imagine Keck will still play an important role to confirm some of these candidates in the Roman era. And lastly, I wanted to briefly mention a related project, a new project we've been pursuing, which is to use Keck to evaluate some of the free proton planet candidates also detected with microlensing. So on the right, you're looking at the event timescale distribution, microlensing event timescale distribution from the recent analysis of the Moser. And most microlensing events arising from stellar lenses occurs in timescale of weeks to months. But there's been an excess of events detected on the timescale of hours. And these are these ultra short timescale events are attributed to planetary mass lenses, relatively isolated planetary mass lenses, down to sub-Earth masses. And the left is an illustration of these kind of events. And these events, so as you can imagine, the sensitivity to these events are extremely low. And after correcting for the detection sensitivity, some recent analysis have indicated that these frequent planet candidates outnumber both the number of stars in our galaxy and the number of bound planets, which is a really exciting result. But there is one catch. In that the absence of a microlensing signal from the host star can only rule out the presence of host star within around 10 AU. If these frequent planets actually bound planets, if there is a host star beyond 10 AU, just because of how far it is from the microlensing source star, it won't be able to impact the light curve. And the way we validate this frequent planet candidate is really similar to our current discovery, which is attempting to directly detect the host light. And in the past summer, we've used the Keck laser guide star AO again to observe some of these candidates, and we have found at least one host candidate, and we propose for additional time next year to see if their proper motion projects back to the microlensing source star, which will confirm them to be associated with the event, namely the true planet host. And that's it. I'm happy to take questions.